So fuel cells. Fuel cells and batteries are clearly very closely related to each other. They both have an anode, they both have a cathode, both have an electrolyte. They differ in that a battery has all its reactants on the inside and a fuel cell has all its reactants on the outside. So it can continue to produce energy as long as you feed it fuel. Now the first fuel cell was invented in 1838 by Sir William Grove. But it wasn't until nearly a century later, with the invention of the hydrogen fuel cell by Francis Thomas Bacon in 1932, that it found commercial application. And of course, when the alkali fuel cell came out, which is also known as the Bacon fuel cell, that was the fuel cell that really took off both metaphorically and literally, as it's the fuel cell that NASA have been using, certainly in the early space launches and to power satellites. Fuel cells are usually classified according to some characteristic or other, like the protein exchange membrane or the solid oxide fuel cell or whatever it is. But they're essentially the same thing, an anode, a cathode and an electrolyte. The material you want to react is allowed to flow across the cell to the anode. The anode has some kind of catalyst on it which will create that reaction, releasing very often the hydrogen ion, which is then able to move across that membrane, because as the ion moves across the membrane, the electrons released move through the circuit and then they're recombined at the cathode when you get something like water and power generation. Nowadays, of course, they're being used in a ton of application, from energy storage to powering buildings and hospitals, backup power. They're used in submarines, forklifts and buses, and they're all over the place and a very active area of research. Now, it was MIT who today released an announcement that they have made the world's thinnest, lightest, most easily sterilizable fuel cell to power medical devices. Now, medical devices actually have a long and interesting history. From the first pacemaker put in 1960 to something called neural dust that's been used in 2016, and the power source for them has always been an issue. The early power sources were fuel cells. They were polymer electrolyte fuel cells. Then of course we got the lithium-ion battery. For a brief period we had radioactive batteries, but there's always been a drive for a fuel source or a supply of fuel to medical devices that could be implanted in the body, last a terribly long time, and didn't need frequent replacement. The device itself is about 400 nanometers thick, which is around about 1/100th the thickness of a human hair, and it produces about 43 microwatts per square centimetre, and that is the highest recorded output of any glucose-based device, because the fuel for this is glucose. However, core of this device is this stuff. This is cerium oxide, or ceria, and it's jeweler's rouge. It's actually incredibly easy to get hold of. Now, cerium obviously is a rare earth, but in these terms it's super easy to get hold of because it's just jeweler's rouge. Jeweler's rouge, of course, is a polishing compound. It's what jewelers use to polish their gold, and it's what the opticians use to grind lenses. The use of ceria makes a thing incredibly easy to sterilise because, of course, it'll last up to 600 degrees centigrade. So the anode on the fuel cell reacts with the glucose in, say, your blood. It separates it into two protons, two electrons. The electrons are used to power the device. The protons go to the cathode side where they recombine and form water. They're really harmless. The really cool thing about this is cerium, ceria. The ceria is biocompatible. It's incredibly safe. It's like zirconium, which is used in tooth implants. So it's incredibly safe to use, and it's able at body temperature to conduct protons. That in itself I find fascinating and useful. The device is awesome. I mean, it's a super thin device that can be put into the body because it doesn't have to account for the bulk of a battery that other devices like pacemaker batteries have to account for. So it is super thin. But for more general terms, the use of ceria as a proton conductor in a ceramic form comes rather neatly to some of the stuff that we've been doing when we're looking at clay proton exchange membranes. Now, normally solid oxide fuel cells need to be operated at high temperatures, in sort of the 500 to 1000 degrees centigrade, in order to get their ceramics to be ionically conductive, to let those protons pass. And that's things like the Bloom box that Google put in one of their office sets over in California. And that's been the state of play for absolutely ages. Now, one of the things that strikes me very often is that what we tend to do is we tend to look quite narrowly at what we're interested in. So I was thinking about wind turbines or batteries. What we do is put in the search term wind turbines, batteries. But if you open that scope into something like biomedical research, you'll find that in biomedical research some really exciting things are going on, and we've got a solid oxide that could be usable in a much larger version of a solid oxide fuel cell and bring down that operating temperature to body temperature. Now, to me, that's a huge breakthrough. And when I read about this, I was reading about how incredibly thin it was, and wasn't that amazing? And yes, it is incredibly thin, and yes, that is amazing, but I don't think that's the relevant point here. The relevant point here is the oxide they used as the solid, this membrane in their solid oxide fuel cell, and that's Cerium. If we start to look at Cerium mixed with clay, then we can make ceramic plates that would operate, or this is the idea, that would operate at room temperature and produce a fuel cell that we could do something the size of the Bloom box with, and yet get rid of that need to have a high temperature. That was what I found fascinating about this particular article. So very often, I think the main takeaway from this isn't the wonder of the thing, but the direction it can give you. Now, the article is this. And it's an open access article, so anybody can actually just go there and read it and find out what these chaps were doing and what kind of results they got from their experiment and how they actually built it. And it's quite a simple build. It's certainly a build within the realms of possibility for a adventurous kitchen scientist. Anyway, I wanted to share that with you because it came out today. I read the thing about the Cerium and thought, oh, that's so useful. I hope you found it interesting. I hope you enjoyed the video, and thank you very much for watching.